500 million tweets per day. In 2007, Twitter went down for almost 6 days. The servers couldn't handle the traffic. They just collapsed. A message appeared. The fall whale. For 6 days of downtime to 500 million tweets per day, what happened in between? Today I'm going to show you 3 things. Why Twitter's original architecture inevitably broke. The engineering decisions that were made, one problem at a time. The full journey of tweet, from the moment someone posts it to the moment it appears on your timeline. One server, one code base, one file with no way out. In 2006, Twitter was a simple app. Built in Ruby on Rails, they call it monolith. One web server, business logic, database, all together, all on the same machine. Post a tweet, same code. Load the timeline, same code. Follow someone, same code. And it worked. Just not for long. From 2008 to 2009, growth was absurd. Each server handled 200, maybe 300 requests at most. CPU and RAM started to cry. But the problem wasn't just the capacity, it was coupling. The same process rendering the web page was also connecting to the database and serving the API. One heavy query, it could freeze everything. A spike on the web, it could bring down all the database connection. It's like a city with only one road in. Accident happened ahead, and the whole city grinds to a halt. There is no way around it. Everyone stops. The first reaction was obvious. Buy a bigger machine. More CPU, more RAM. In hours the capacity doubles. Looks like the perfect solution. But there is a physical ceiling. Doubling capacity costs 3 to 4 times more. And it's still just one machine. If it's going down, the entire operation stops. The answer was horizontal. Multiple smaller machines running in parallel, with a load balancer up front. To the user there is just one address. They don't even know there is a multiple servers behind it. But if new servers run the full monorail, the same code solves capacity, doesn't solve coupling. And a new problem appeared. Session. User logging on a server A. Session lives in A's memory. Next request goes to the server B. B says, "Who are you? I don't know you." Fix? Move the session out of the server. Put it in a shared memory database. Now any server can handle any request. Rule that applies for the rest of this video. Stateless server. No data in local memory. Can be destroyed and recreated without losing anything. To scale, just add more. Cache, replicas, sharding, and specialized database. The web servers were scaling, but all of them were hitting the same MySQL. Everything in the same database. Tweets, user, follows, timelines, and the heaviest operation of all, building a timeline. You follow 500 people, the database needs to fetch tweets from each one, cross-reference author data, sort by date. A massive join across 3 tables with billions of rows, running every time someone opens the app. First defense, cache. If the timeline hasn't changed in the last few seconds, don't recalculate it. 8% hit rate. The database automatically receives 8% less load. It just becomes the home of timelines, a list of up to 800 tweets per user. Reading timelines is a get, milliseconds, but cache represented only 3% of the infrastructure. But it was the most critical component. Cache goes down, every request hits the database directly. Cache stamped. Next layer, read replica. Primarily accepts reads and writes. Replica service reads only. Twitter is a massively read heavy. Replicas multiplying read capacity without touching write. And writes, sharding with Gizzard, a middleware that wrote each write to the write shard. With one requirement, our write had to be idempotent. Resending produced the same result. No duplicates. Save retrying in any distributed system. And when the relational model couldn't keep up, specialized database came in. FlockDB for the social graph. Who follows who? Snowflake, unique IDs, 64 bytes, embedded timestamp, no central coordination. Manhattan, distributed key value, which become the main storage layer. Cache first, replicas next, sharding last. Specialized database only when the relational model couldn't get there. From asynchronous to async, and the problem of massive accounts. Until now, everything was synchronous. User posts, server process everything, then response. But everything includes notifying followers, delivering by SMS, indexing for search, updating counters. If you had to wait for all that to tweet, you never tweet. Solution? The couple receiving from processing. The service accepts the tweet, responds immediately, and throws the task into a queue. Works handle the rest. Twitter built Kestrel, an open source message queue written in Scala. The queue observed spikes, 10,000 tweets in a second. Works don't need to process 10,000 in that second. Works dies, message goes back to the queue. Kestrel only removed an item when the worker confirmed it was processed. Nothing was ever lost. With the queue in place, Fanout becomes possible. The problem: when someone posts, how does each follower's timeline get updated? Fanout on read. You calculate when someone asks. Posting costs nothing, but every time someone opens the app, the system feeds tweets from everyone they follow, joins, sorts, delivers. 300,000 times requests per second, against 6,000 writes. That's 50 times more reads than writes. Fanout on write. Flip the logic. Do the hard work when the tweet is posted, so reading is stunted. Someone posts, Fanout service looks up every follower in the FlockDB, drops the tweet ID into each one's Redis timeline. When the user opens the app, it's already there. 1 get milliseconds. The work was done the moment the tweet existed. But accounts with millions of followers, 10 of millions of operations per tweet. Twitters took up to 5 minutes. A reply could arrive before the original tweet. Solution? Hybrid. Normal accounts, Fanout on write. Large accounts, Fanout on read. Tweet stored once, fetched on demand. When the app opens, the system merges both sources in milliseconds. Not clean, 2 code paths, but it handles both extremes. 2010 World Cup. Every goals, every red card, every penalty kick, a wave of tweets. And Twitter went down, repeatedly. The diagnosis? It wasn't the number of machines, it was the monoarray. The code itself was the problem. Tweet migrated to the JVM, Java and Scala, 3 times reduction in search latency, and the composition in services, tweets, user, timelines, Fanout, each independent. Dozens of services bring 3 immediately problems. How does one service find another? Hardcode headers don't work. The service can scale, change machines, go down and come back somewhere else. Zookeeper adds service discovery. Each service registers on startup. Others queries it and get the current address. What happens when a service fails? Requests pile up. Timeouts, callers get stuck to, cascade failure, circuit breaker. If the last end request failed, stop sending and returning an error. After a timeout, send a test request. If it works, close and return to normal. They implement it per node. One failing FlockDB server got isolated. The others keep running. Timeline is low. Which server is the culprit? Dozens of calls in a single request. Without tracing, impossible to know. Twitter builds Zipkin. Each request gets a trace ID. Each service records how long it took. You see a visual timeline of the entire chain, exactly where the time went. The Fallaway was retired around 2013. Zero downtime in 7 of the 11 months that year. From phone to timeline altogether. Now let's put it all together, the full journey of the tweet. The tweet leaves your phone. The connection terminates at the nearest edge server. From there, it goes to the data center. Load balancer, stateless web server, tweet services via Zookeeper, tweet store it in Manhattan, ID generated by Snowflake, 64-bit embedded timestamp, no central coordinator. The tweet exists, but nobody knows about it yet. It goes into the Castro queue. Fanout services query FlockDB, insert the ID into each follower reduce timeline. Larger account? No Fanout. Pull it on demand layer. Index for search, process notification, all async. On the other side, someone's open app. Add server, data center, load balancer, web service, timeline services via Zookeeper, circuit breakers rewrote if a node is failing, Redis delivered the list of IDs. Large account, merge it on the fly. Full content hydration, images and videos from CDN, timeline delivery in milliseconds. 300,000 times per second on read, 6,000 on write, 500 million tweets per day. Nobody designed this architecture all at once. It was born from problem to problem. Service couldn't handle it, scale. Database lookup, cache. Cache wasn't enough, replicas. Write saturated, sharding. Everything synchronous, queues. Monolith couple everything, microservices. Services cascading, circuit breaker. No visibility, tracing. Every new layer solved a problem and introduced complexity that didn't exist before. And that's exactly what I want you to take from this. Start simple. Don't build for a scale that may never come, because every evolution brings new problems, and solving problems that don't exist yet is waste. Involve when the problem is real, not because you want to be ready for everything. If this video gave you value, hit like and tell me in the comments what's the next architecture you want to see here.